Good afternoon. On behalf of the Southampton Theory, Astrophysics, and Gravity Research Center, I would like to welcome you to this year's public lecture. My name is Kostas Kenderis, and as a director of STAG, I will be your host this afternoon. We would have much liked to welcome you in our beautiful campus, which you can see behind me. But unfortunately, due to the pandemic, we cannot do live events. So we instead decided to hold this virtual event. And I now have the pleasure to invite Professor Mark Spearing, the Vice President, Research and Enterprise of our university, to open this year's STAG public lecture.
Thank you very much, Kostas, and welcome everyone on behalf of the University of Southampton to this year's STAG lecture. This lecture epitomizes the strength of our university's commitment to excellence, interdisciplinarity, and diversity in the areas of research that our community pursues. The lecture, the topic is very much about fundamental science, but at a universal scale, utilizing techniques at the interface between mathematics and physics, with the potential to reveal answers to fundamental questions about the alpha and omega of our existence, as well as to inspire a wider public and future generations. I note that at the moment, physics seems to be very much in the news on a nearly daily basis, with excitement in gravitational waves, ever more curious cosmological structures and events, new fundamental forces, hints of new particles, and hitherto theoretical quantum phenomena being demonstrated experimentally. It is a very exciting time. These annual lectures are run, as Kostas said, by our STAG Research Centre. For those who do not know, the Southampton Theory, Astrophysics and Gravity Research Centre aims to foster and promote cutting-edge research on fundamental science, from the very small to the very big, from the fundamental microscopic building blocks of matter to galaxies and the universe as a whole. The STAG also, completely coincidentally, is the heraldic symbol of the University of Southampton. Go figure. As part of its mission, STAG organises several high-profile scientific meetings and lectures every year. A recent success was a meeting on the accelerated expansion of our universe, which attracted over 200 participants from all over the globe and featured speakers from Princeton, University of Chicago, and many other institutions. Another part of its mission is to promote public awareness of fundamental science and to inspire the students of today to become the scientists of tomorrow. STAG also notably organises this annual public lecture, which is always given by a highly distinguished researcher on a topic that explores and explains great achievements in fundamental science. This year's speaker is eminently qualified to join the distinguished list of previous speakers, all of whom have been winners of major prizes, including 4 Nobel laureates. So on behalf of the University of Southampton, I'm delighted to welcome Professor Jim Gates, who will deliver this year's lecture. Since I'm not qualified to do justice to Professor Gates's qualifications, I'll hand back to Professor Kostas Skenderis to introduce our speaker formally. Kostas, over to you.
Thanks, Mark. So very much delighted to have Professor Jim Gates delivering this year's online STAG public lecture. Professor Gates obtained his PhD from MIT, and he held previously prestigious positions at the University of Maryland till 2017, where he retired from Maryland, and then he moved to Brown. He is currently the Brown Theoretical Physics Center Director, the Ford Foundation Professor of Physics, an affiliated mathematics professor, and a faculty fellow at the Watson Institute for International Studies and Public Affairs at Brown University. Professor Gates is well known for his work on theoretical physics, and in particular on supersymmetry, supergravity, and string theory. His book on superspace was the first comprehensive book on supersymmetry and supergravity, and it continues to be an inspiration today, even 40 years after it was written. He's also well known for his advocacy for science and science education. He has served on the United States President's Council of Advisors of Science and Technology from 2009 to 2016. He was on the Maryland State Board of Education and the National Commission on Forensic Science. He has been elected in numerous prestigious societies and academies, for example, in the National Academy of Sciences. He was a past president of the National Society of Black Physicists, and he is the current president of the American Physical Society. He received a number of awards, including the 2011 National Medal of Science, which is the highest award given to scientists in the United States. He's also been active in educating the general public about science. He co-authored science books aimed at the general public. He completed a DVD series on string theory for non-physicists, and he continues to broadly engage video documentaries with appearances or cameos. We're very much honored to have Professor Gates delivering this year's lecture, and I'm looking forward to hearing about people no one can imagine anything of. Please, Professor Gates.
Thank you, Kostas, and let me get my video on. First of all, I'd like to greet your audience. These days, events like this are often asynchronous, and so one doesn't know whether one should say good morning, a good day, or good afternoon, or good evening. So I'm saying all of those in case you have some folks who are tuning in from various parts of the world. I know I talked to some friends in Australia about this presentation, so we have to dispense with thinking about time locally. So what I'd like to do, first of all, is to thank Kostas and his colleagues there at the University of Southampton for this opportunity to speak to you. I, as Kostas said, speak broadly to the public. In fact, there is a documentary about the life of Stephen Hawking. It should be out in the fall, and there's a picture of me in 1980 visiting Cambridge, which hung on Stephen's wall. So when the documentary was being prepared, the producers saw the picture, and they saw one guy in the picture with a really nice tan. And so they reached out to me, and I'll be in that film too. I got word from the producers the other day that they're in final post-production work. So you should keep an eye out. This film was actually commissioned by Stephen's family. So let's get started on today's journey. So I'm going to share screen. Here we go. And go into full. There we go. People no one can imagine anything of is my title. And I take this title from two prospective individuals that I have a high regard for. First of all, there's what I call hero Maximus in physics, namely Albert Einstein. And Albert once said that imagination is more important than knowledge, for knowledge is limited to all we now know and understand, while imagination embraces the entirety of the world and all there will be to know and understand. So I emphasize now and will be, because notice that Einstein talks about the importance of knowledge. It's what we know now, but if we're ever going to have more knowledge, we need imagination to get there. Another famous person for whom I have a high regard is Alan Turing, the computer scientist from the UK, who unfortunately, worked at Bletchley Park during World War II, helping to decode the Enigma machine, which was a major breakthrough in the prosecution of the war against Nazi Germany. But also, he had a troubled life because of difficulties around that time around his sexual identity. And he had a very tragic and short life. And I would commend anyone to read about this towering genius in computer science. But one of the things that he said was, sometimes it is the people no one can imagine anything of who do the things no one can imagine. And so taking these two quotes as my touch points, I'd like to proceed. So Albert Einstein was the man of the century in Time magazine in its last issue of the last century. And this is one of my favorite pictures of Albert Einstein, so I just like to use it. Here's another picture of Albert Einstein you probably don't know about. In 1946, long after he had stopped going to receive honorary degrees, he made an exception in 1946 to go to an African-American university called Lincoln College. It's outside of Philadelphia. And this is a picture of a lecture he gave on relativity to a group of the students who attended the school. Albert Einstein, in fact, had fairly deep connections to the African-American community. He recognized similarities in the conditions that community faced in comparison to the conditions that he faced as a young minority Jewish child growing up in Germany. And he had a close friendship, as one example, with Miriam Anderson, a famous contralto singer. And in fact, when she would visit Princeton, he offered her his home as a place to stay because she could not get lodging in a local hotel. So, Albert Einstein, I'm going to tell you first about the things that I first heard about this guy when I was 17 years old. I learned about his theory of special relativity, and it's about a bunch of math. But since this is a public lecture, I always like to tell people, please don't bring out the holy water, because the math that we're going to encounter will be fairly infrequent in terms of the discussion. But I at least want to show you that math is in fact the fundamental language that we physicists think in terms of. And so this was his first set of equations written in a very special form that emphasizes geometry. But the importance about mathematics and physics is that we use it to tell stories, just like a novelist uses language, punctuation, and sentences to tell stories. We tell our stories in mathematics and theoretical physics. So what is the story behind this? Well, first of all, he observed that, like Newton, space-time could be thought of as a kind of a grid. That's what I'm showing you in this image. However, he went beyond Newton because in Newton's point of view, this grid had a certain fixed property, but for Albert Einstein, it was flexible. He said this grid can flex, and because of that, our notions of space and time must change. Things can shrink when things go fast. Clocks slow down when things go fast. Things that you used to think happen at the same time in one frame of reference can happen at different times. And the only thing that's constant in this is the sloping shape of those yellow lines, and that represents the speed of light. So that was what was behind Einstein's first enormous contribution to physics, which occurred in 1905. It's called the Year of Miracles. He wrote 4 papers that year, and every single one of those papers could have won a Nobel Prize. One of them actually eventually did, but it's not for relativity. It was for talking about the interactions of electrons and photons, particles of light, for which he won the Nobel Prize eventually. It was only one of these 4 papers, but the other 4, 2 of which include relativity, one of which has a famous equation, E equals mc squared, were all done within a year while he was in the patent office working as a clerk. So that was 1905. Now, you might think someone who had such a miraculous year would immediately be recognized as a genius and given a faculty position. So when 1907 rolled around, guess where Albert Einstein was? Still in the patent office. One day while he was in the patent office, the story goes, because he tells the story, he looked out the window and there was some workmen working on a roof in an adjacent building. And he had the thought that if one of those workmen were to fall off the building, they would not feel their weight. He called this the happiest thought of his life, not because he was some kind of wishing ill for another one of his fellow human beings, but because he understood from thinking this single thought that gravity and acceleration must have something to do with each other. And it's from here that he took inspiration to ultimately create the theory of general relativity, which I like to call Einstein's Opus Part 2. So I've written, again, a few of the mathematical equations, but don't worry about it. We're not going to be using them, but it's like looking at a score of a beautiful piece of music. At least you should know the score exists. And so this is what the scores look like to Albert Einstein's ideas. Again, let's use some pictures to dig into these. So the first of Albert Einstein's ideas is that gravity can be mathematically visualized as if one has a rubber sheet and you put objects on it that cause indentations, and then gravity is actually the bending indentation. So the sun in this picture creates an indentation around itself from its gravity. The earth moves, but it also creates its own indentation. And in this image that we're watching, this is the indentation that keeps the moon orbiting around the earth. And so the earth moves in the indentation of the sun, the moon moves in the indentation of the earth, and that's how gravity works. And that's what these equations explain. Now, what's really interesting is that in order to get here, you had to use this notion of space-time that I showed you earlier. Albert Einstein did not actually introduce that notion. His teacher, Hermann Minkowski, did. So the mathematics that we use these days was not, it was inspired by Einstein, but its fullest realization is by a host of other people around him. Now, a few years ago, I wrote a book with a co-author named Kathy Pelletier. The title of the book is Proving Einstein Right. And the reason I want to touch on this is because now, of course, you've heard of the Big Bang. You don't think it's unusual. You've heard about black holes. But when Einstein produced his work, no one had heard of those things, except possibly one individual. There was a clergyman, philosopher, scientist named John Mitchell, who lived in England. And he is, in fact, the first person to have the idea of a black hole about 125 years before Einstein ever appeared. But at the time that Einstein physicist finished his work on gravitation in 1915, most people, in fact, most scientists were befuddled by his mathematics. And so this book is basically a telling of the story of how his mathematics got to be understood by the scientific community as an accurate description of the universe. So it's about eclipses, because in order to prove Einstein right that first time for the scientific community, you had to verify one of his predictions from general relativity. Now, he made several predictions. One of them was about the way that Mercury orbited the planet. The way Mercury orbited the sun, and that prediction was actually a post-prediction, because using Newton's theory of gravity, you couldn't figure out why Mercury moved like it did, but using Einstein's form of describing gravity, it was in agreement with what nature did. A second prediction was about the behavior of a light as it moves either toward or away from a large gravitating body. In fact, you get a shift in the frequency that is very similar to a Doppler shift. And then the final one was that light would be bent by the sun. So he made this prediction in 1915. He needed to try to get proof, but he couldn't get proof by working by himself. He started to reach out to astronomers. And the first astronomer he reached out to was a German astronomer named Edwin Freundlich. And they got, from the astronomers, Einstein got the idea that you could measure the bending of starlight by looking at stars during an eclipse and looking to see how the light bends in the presence of the sun. Between 1900 and 1922, we, in our book, talk about how groups of astronomers went all over the world trying to verify this prediction. And this is an actual photograph taken from the Eddington expeditions of 1919, which were the first to actually measure this bending starlight. And so the real heroes of general relativity, the people who turned it from mathematics into science, was this list of eight astronomers, and of course Albert Einstein himself. But mostly the names on this list are lost to most of history, except for perhaps Sir Arthur Stanley Eddington, who was Astronomer Royal. He's actually the person who led the expeditions, as well as Sir Frank Watson Dyson, who was the preceding Astronomer Royal before Eddington and had offered support. But this is the list of people that turned the math into science. What science did they give us? Well, they gave us equations that are so powerful that scientists can now tell you about the history of the universe. According to our present view, based on Albert Einstein's equations, there was a special instant when all potentialities of everything and space and time and happening in the future all existed at this single location. This location is now called the Big Bang. But the thing to keep in mind is that as I'm telling you the stories, what I'm telling you are about the properties of equations. The Big Bang is a solution to a set of equations. So the universe starts with the Big Bang. There's a period of about 380,000 years where light is not free to pass through the universe. But at about 380,000 years, the universe cools sufficiently that it becomes transparent to light. And that is called, that surface that happened is called the cosmic microwave background. And we see the cosmic microwave background to this very day by looking up with instruments tuned to microwave frequencies of electromagnetic radiation. There was another period when the first stars were coalescing, and then they turn on. And now our universe begins to evolve into the place that we know it. It went for a while with a steady rate of expansion, and then that expansion started to speed up about a couple billion years ago. And we call this speeding up period of expansion, or the acceleration of expansion. We think it's caused by something we've named dark energy, but it's rather mysterious and we don't know the full answers. Einstein's equations actually talk to us about 5 different ways the universe could have begun. It's not doesn't give us a single solution. And in fact, when Einstein first solved them, he thought that our universe was like a soap bubble. It was always there. And in order to describe this, he introduced a number that he called the cosmological constant. And, you know, it said, well, the universe is eternal and unchanging. And my equations prove that. Well, if he had not introduced that constant, something very interesting would have happened. Namely, the universe would have, show you these cartoons again, the universe would have come into existence, but it would not be a static bubble. It would be expanding or oscillating if that constant that he introduced was 0. And then finally, if you make the constant positive, the universe comes into existence and expands, but it accelerates. And this is called a de Sitter geometry, and that's what 20 years ago we discovered our universe looks like. So I'm a particle physicist, not an astronomer and not a cosmologist. And so I'm, as was mentioned in the introduction, talking about the STAG Center, those of us in fundamental physics think about very large things like the universe, but we also think about small things. And that's really where I've spent my career. If you ask what is there, if we look at our most powerful scientific instruments and ask what does matter consist of, what does our universe consist of? Well, atoms have electrons in them, so you see them illustrated here. Nature is very peculiar because she also has produced things that are like neutral electrons. They're called neutrinos, and you see me toggling between the neutrinos in the image. However, nature also copies herself. So in addition to the electron, there's another particle that it has 200 times the mass of the electron, but in all other ways it appears to be an electron. It's called a mu particle. And then about 30 years ago, we discovered that nature has a third copy of the electron. It's called a tau particle. It's about 1,700 times as heavy as the electron. There are quarks, up and down quarks, so how you get to make protons. They come in different spin sectors, so that's why I've doubled them. And everything is held together mostly by electrical forces if you're doing chemistry, and there's a carrier of the electric force, the photon. The quarks stay inside of the nucleus. They are held there by 8 force carriers called gluons, and then finally, the weak nuclear force has 3 carriers, the so-called Z0 and the W plus or minus. And then finally, the weak force has one other carrier. It is called the Higgs Boson, which you've probably heard a lot about since its discovery at the LHC. So I like to show this image to people, and what we've done is we have one column to the left, and in this leftward column, it turns out that no 2 of those objects can be placed at the same time at the same place. There's something called the Pauli exclusion principle that applies to everything in this left-hand column. On the other hand, believe it or not, photons actually can pass right through each other. And that means you can put as many photons as one place at one time as you wish. And if you turned out all the different kinds of charges, that would apply to the other particles in this rightward column. So that's what we know from several hundred years of science, asking what is there that we can detect in our instruments in the domain of the very small. So I like to ask people when I show them this image, does this look very pretty to you? Is it symmetrical? Now, most people will say no. And so I said, well, what about this? Oops. What about talking about this property of the left and right-hand columns? What distinguishes it? Well, it turns out that all those particles actually spin. They act like little spinning balls. And the rate of spin, we typically denote by the symbol S, and it is characterized by Planck's constant squared times a quantity which takes values either 0, half integers, or integers. And every particle, turns out, has a spin that's governed by this. Now, the things that were in that left-hand column, like the quarks and the electrons, spin with a value of J equal to 1/2. And we call those fermions. all the things in the right-hand column spin with rates either 0 or 1. And so we call them bosons. And so that split that we saw before is really about spin. Now, the Higgs boson, which I talked to you about, when it moves, it obeys the equations precisely of a spring or a slinky or a sound wave. And I have a cartoon here illustrating a slinky. And so when a Higgs boson moves, you can visualize that motion as being a clump of something moving as if it were on a slinky, a toy. On the other hand, when the photon moves, it moves in a very different manner. In this image, on the left-hand side of that quarter wave plate, we see a wave going up and down. That's a wave of light. The quarter wave plate I use to separate the beam of light, and I can separate it into a right-handed circular polarization, which is the upper, or a left-handed circular polarization, which is the lower image that you see. So when these small particles move, you can distinguish them by the kinds of wiggling that they perform as they move. So here's that table again, and I'll come back. Is this table pretty? Is this table symmetric? As I like to say, normally people say no. I think that's the right answer. It's neither. But what about this table? What if the universe actually looks like this, not like what we've seen so far in experiments? You can see there is a left-right symmetry as you view this image. Everything that you see on the left-hand in the center line has a mirror copy on the right-hand side. Now, from experiment, this is what we have seen based on several hundred years of experiment. In fact, the idea of the electron goes back to a Scottish electrochemist named J.G. Stoney. A lot of people know J.J. Thomson's name associated with the electron. He didn't invent the notion. He just measured some of its properties and verified that such an object exists. But the first person to conceive of the electron was J.G. Stoney, and he even gave it its name. But back to our more symmetrical universe, suppose the universe really looks like this. Now, why would you even have this idea? Well, I remind you that we didn't always know about the Higgs boson. And it was the actual scientific verification of the Higgs boson is less than a decade old. So when we look, we always are limited by the quality of our technology. And as our technology increases, our ability to study the world increases and we find new objects. So one could imagine that at some point in the future, our technology would be sufficient so that we could detect all these other objects that have this nice symmetry. Now, these other objects are called superpartners. And this is where I have spent my entire scientific career studying the mathematics of these kinds of objects. Do I know that they exist? No, but I have a very strong suspicion that at some point in the distant future, we're going to find these objects. I wrote the first PhD thesis at MIT on this subject in 1977. And at the time, no one at MIT had any interest in this sort of mathematics. So I had to teach myself basically, which was a really interesting experience for a graduate student. What about gravity? Well, you see, what I've been telling you about with that table is called the Standard Model. And the Standard Model does not provide a description of gravity. General relativity provides a description of gravity. And those are two different sets of mathematical equations. In fact, if you try to combine the two, you run into some problems that we'll come into later. But what does a graviton do when it moves? Does it move like a slinky? Does it move like a particle of light? The answer is no. It actually moves in an entirely different way. And I use this cartoon to show you that type of motion. So imagine that you're looking down a tunnel, a perfectly circular tunnel, and a gravity wave comes from the back of the tunnel towards your eyes. And you had detection devices in the tunnel to measure the effect of the graviton. This is what you would find. You see, it deforms the tunnel. Now, when there's no gravity, it's a perfect circle. But when the gravity wave comes through, it takes the shape of the circle and deforms it, as you can see in this cartoon. So this is the gravity equivalent of a linear polarized gravity wave, analog to our linear polarization on light. If you try to look at its helicity states, life gets more interesting. If you look at the counterclockwise winding helicity states, it does this to the tunnel. So no graviton, graviton wave moving through. As you can see, it's a nice sort of oscillating oblong shape that rotates. What about the other helicity? What does it do? Well, it rotates in the opposite sense. So these kinds of computer illustrations I'm showing you, we don't have the technology yet to measure these. What we've measured is just the linear polarization, but when we measure these, we will be able to verify a prediction from Einstein's theory of general relativity that the wiggling that I described to you here, which we know about on the basis of mathematics, actually occurs in nature. And so that will be another feather in Einstein's cap with regard to describing gravity. So Albert Einstein did a lot of great physics in his life, and one of the pieces of physics which he's responsible for but never took credit for is what we call quantum mechanics, because the 1905 paper that he wrote, which actually won him to become the recipient of the Nobel Prize, that paper is about the photoelectric effect, namely how electrons and photons interact. And what the paper explains is an experiment where you shine light on metal and then watch electrons being ejected from the metal. And the peculiar thing is that the electrons are ejected not at all energies, but at very specific energies. And so Einstein explains this by writing a paper where he explains that energy, as carried in by the photon particles, comes in packets. In other words, the energy is quantized. So Einstein's 1905 paper is one of the most powerful evidences that quantum mechanics was real, not just a piece of mathematics as discovered as proposed many years earlier by the German physicist Planck. So Einstein, if we look at quantum mechanics and think about our elementary particles, Newton says things basically, if you leave them alone and throw them and there's no influence, they move in straight lines. Whereas according to quantum mechanics, something different happens. Now, when we think about our particles, so this is a cartoon here where on one side, I have a track for an electron moving. On the other side, I have a track for an electron moving. And in between, they exchange a particle of light, which tells one electron it ought to be repelled from the other. So there's a photon saying, you need to move away from me. And we can see it again. And so this is how we visualize forces working at that classical level. When particles would move in straight lines, we say, this is how the electromagnetic force works. Now this image is called a Feynman diagram. And those of us in particle physics actually use this image to calculate very complicated integrals. Remember, I told you my storytelling is based on math. So every image I showed you is actually backed up by a set of mathematical equations. So this is classical electromagnetic repulsion according to physics. And if you use Mr. Feynman's rules, you can show that the repulsion goes like 1 over the square of the distance, which is known as Coulomb's law. But in a quantum mechanical universe, if you try to throw an object from one location to another, it could move on all kinds of jagged paths before it gets there. Because in quantum mechanics, even with no influences, things do not move in straight lines. So let's apply this idea to the forces. It turns out that here's another more complicated diagram. And the outside of this diagram, again, shows one electron moving, a second electron moving. And this electron will emit a photon to the first electron will emit a photon, which tells the second electron to be repelled. But in between, it also emits a photon that it absorbs. So let's watch this one, except that my animation failed me there. But here's another non-classical expression at work. Here we see an electron that sends a particle of light that decomposes into an electron and its antiparticle. They have opposite charges, so they attract each other and destroy each other, create a second photon, and it's this second photon that tells the second electron to be repelled. Now, there are actually an infinite number of these more complicated diagrams. And so you might wonder why physicists believe that such things are possible or even apply to our universe. So let me take you on a little journey. It turns out that the electron behaves like a tiny magnet. And if you measured the strength of the electron only using the laws of classical physics, you would find out that it has a strength that in certain units we can call the number 2. But as you can see, what I've written here is not just 2, it's 2 and all these digits afterwards. So where do those extra digits come from? Well, remember I told you that there are hundreds and hundreds of these Feynman diagrams? So when you calculate the magnetic property of the electron, you have to take the contribution into account for all of these diagrams. In fact, we've been doing this for 40 years using computers. And so you can measure this in a laboratory, and you find out that it's not just 2, but there are all these corrections to the 2. If you measure it using Feynman diagrams, you can also calculate, and you'll notice that up until these last 2 numbers, everything else here, which is the measured value versus the theoretically calculated value, are in precise agreement. This is better than 1 part in a billion agreement. And this is the only piece of science where we have a theory that agrees with observation to better than 1 part in a billion. Now these last 2 digits disagree, but that's because it's what we call the uncertainty. And in physics and in science in general, we cannot make infinitely accurate predictions nor measurements, but we can do it with an increasing amount of accuracy. Now, this kind of experiment was recently actually in the news, because not only does the electron behave like a small magnet, so does the mu particle. That copy I showed you, that was 200 times as heavy. And so the mu particle also was recently had its magnetic property measured, and its measurement seems to disagree with what we would predict on the basis of the particles in the standard models, which were the particles I showed you. It looks like there's some additional contribution. And so a lot of physicists are very excited about this, because this may be pointing to that second table I told you with the superpartners. Now, it doesn't necessarily have to be the superpartners. Maybe there's some other collections of things out there, but it's the first indication we have, if this experiment holds up, that there is more to the universe than the standard model. Okay, so why did I take you through? So what did we go through? We reviewed general relativity and gravity. We reviewed a little bit of classical physics. We reviewed particle physics, and we reviewed quantum mechanics. And now I can set you up to what my question is. It's about the search for quantum gravity. You see, our universe is such that we know that it obeys quantum mechanics to better than 1 part in a billion. But we also know that general relativity really works well. And one of the ways we know this is by looking at the black holes that occur at the center of galaxies. So M87 has a black hole, but so does our galaxy have a black hole. And there are stars that orbit that black hole. And so you can use the orbits of those stars to test general relativity. And so far, everything works just fine. Instead of thinking about the Earth orbiting the sun, you can think about the central mass here as being a huge supermassive black hole at the center of our galaxy. And then instead of the Earth, you say, aha, I'm following the orbit of a star around that mass. This was the reason this year's Nobel Prize was given. It was shared by Roger Penrose, a British physicist who showed that black holes form whenever the conditions allow from Einstein's equations. And then Andrea Getz and Heinrich Gensler were people who used very powerful instruments to observe stars orbiting the center of our galaxy and proving that there was something there with a mass of several million suns. So we know that both sides of these, the mathematics on both sides of the pictures I'm showing you work exceedingly well. But if you try to combine them, they actually fail. If you try to make gravity quantum mechanical, it turns out that mathematics makes no prediction. And so it has been a task to try to find a theory that actually includes both of these. And the person who most pointedly directed us along this task was Stephen Hawking, who pointed out that black holes have other properties that make it impossible to ignore their quantum structure. So quantum gravity is something that we have not completely succeeded even to this day. We're still working. But in 1995, Edward Witten proposed that the 5 known string theories, the type 1 string, the heterotic string, the E8 string, the type 2A string, and the type 2B string, could all be combined with one other theory called an 11-dimensional supergravity, and that all of them together constitute a description of the quantum gravity that we're looking for. So if you look at 11-dimensional supergravity, it's, well, once again, folks, I remind you, it's really mathematics. That's what all of these stories are about. 11-dimensional supergravity is relatively simple. It has something that's like a graviton. We typically denote that by this symbol you see here. It also has something that's rather similar to an object that's kind of like a photon, but it's got more indices. A photon only has one of these indices, whereas this thing has three of them. We call it a three form. And then there's a particle that is like an electron, but except that it also carries an index like the photon. And this is called a gravitino. So that's the theory of 11-dimensional supergravity. So what's the puzzle I'm after? Well, the puzzle goes as follows. If you don't use quantum mechanics and you ask, are there how many different ways the gravitino can wiggle? The answer turns out to be 128. Remember when I told you the story of the photon, there were two different ways to wiggling? And when I told you the graviton story in 4 dimensions, there were two different ways of wiggling? Well, in 11 dimensions, which is mathematically where this thing lives, there are 128 ways this object can wiggle. On the other side of our transparency, we have these two objects, and what we find for them is that for the first there are 44 different ways it can wiggle, and for the second there are 84. Now, why are these numbers important? Well, remember in supersymmetry, you always had that left-right balance? Well, if you take 44 and add to it 84, it exactly equals 128. And so that's evidence that this theory is supersymmetric. But is it always supersymmetric is the question. And the way that we can answer that is to ask, when this object is not obeying its equation of motion, how many different ways does it have to wiggle? The answer turns out to be 320. What about for these other two objects when we look at them when they're not obeying their equations of motion, when they're not following the classical path? Then you find out that there are 66 ways that the first one can wiggle and 164 that the second wiggle. If you try to add these up, you'll find out they do not add up and equal to each other. And so that means that if you're doing quantum mechanics on these objects, it's not supersymmetric. But supersymmetry, we think, may be something very important in our universe. And so the question is, how do you solve this problem? How do you allow Witten's theory to have the sufficient number of degrees when you're not obeying the laws of classical mechanics? How do you get that to work? Well, one thing, this wiggling that I keep talking about has a description in a set of figures called Young to blows. And remember, I'm going to take you to the description with a little bit of mathematics. And so mostly I'm going to be talking about graphics. So these kinds of pictures are important. In fact, on the left-hand side of that image, I have, actually I just noticed that Young to blow is not correct. The bottom box should not be there. It should just be the two upper boxes. These two things provide a description of this object. The two boxes in a row here provide a description of this, and the three vertical boxes provide a description of that. And so this is a problem that was first thought about in 1973 and 1976, and people figured out how to solve it. What you do is you add more stuff to the theory, and that's the question is that I'm after is the work that was done in 4 dimensions, can we extend it to Witten's theory of M theory, which is supposed to encompass all string theories. So that's my goal. This problem has been around since 1995, and no one has ever solved it. So as mentioned in the introduction, in 2017, I changed my academic home from the University of Maryland to Brown University, where I currently work and teach. And one of the things that I was thinking about was this problem. Now, I was also very fortunate because I have these two fantastic graduate students. One of them is Cesnin Hazel Mott, and the other is Yangre Hu. And we started talking about these problems. And all of a sudden, I started to get some new ideas. And that's what we're going to finish up on, these new ideas to solve this problem. Well, first of all, these ideas sort of come from, in some sense, from biology. All of you have heard of DNA. Well, the first person to know the structure of DNA was this woman, Rosalind Franklin. She was an X-ray crystallographer working at Imperial, if I remember correctly, and she discovered the double helix structure of DNA. Now, one thing about DNA is that naturally, these are representations of it, but it naturally is kind of a network. A network is something that has nodes and connections of those nodes. So if you, for example, you can think of this point as a node, and you can see it's connected across here, and it's connected along the so-called backbone of the DNA. And so one thing that we know is that because of this structure, for example, because of the structure, we, within a year as a species, found a cure to the COVID pandemic. And it was based on genetic understanding of what the COVID virus looks like. There are online resources that allow you to study genetic structures, and the so-called basic local alignment tool, which I'm actually showing here, BLAST is the acronym, is a way to take a snippet of DNA and to find the whole piece of DNA that it belongs to. So I started thinking about these ideas with regard to my problems, which I had been sort of bumbling along for a while. You know, I talked about dimensions earlier. Well, for someone like me, a dimension is a mathematical property. When the dimension is 4, we're talking about our universe. When it's not 4, then maybe we're talking about our universe, but maybe not. And so in 2004, I started thinking about M theory and asking the question, if we reduce it down to one dimension, what does that mathematics look like? This was in a paper with a colleague of mine named Michael Fox, and we found out that there's some interesting mathematics in the shadows here. The way that this works is we base it on the Einstein's light cone, which says that if you want to study the future, one way to think about that is being an observer. If you send a signal to the future, you can affect things that inside the light cone, and anything in the past light cone can affect you. And so when we do our reduction, we only work inside of the forward light cone. And what we found is the upper part, this is the math that describes 4 dimensions. And again, I apologize for the math, folks. But when you go down to 1 dimension, it turns out that that mathematics is perfectly representable by a network. And what's really cool about these networks is that they are sufficiently close to the structures that people study in genetics that I started thinking about, well, if I had a genetics problem, how would I solve it? So these networks are also deformable. So I just showed you a deformation starting from the top network, and I can deform it and get the bottom network. And that's, so these two things are not, so under this motion that I showed you, these two things are in fact the same object. If we talk about the photon, on the upper part of this, I've shown you the mathematics for the photon. In fact, this object A is a mathematical representation of photon. So it's, again, it's a bunch of mathematics, but can we do this one-dimensional shadow process? The answer turns out to be yes. And we find a different figure contains the information about the photon. There's another object below, and these are also, I can get by deformation. So rather than thinking about the actual equations that Ed Witten and most of my colleagues think about, I have been wrestling with the idea of, can I answer this particular question about having equal numbers of degrees of freedom when the graviton and the gravitino and the 3-form are not moving classically? Can I cast this in the language of networks? These networks, as I said, we invented with Michael Fox in 2005. In a 2010 edition of the UK journal Physics World, our networks were highlighted as the cover story. When you step into networks, it changes your view tremendously of what you can do in physics. And in fact, it also enlarges the amount of mathematics that you can bring to bear. Most of you know about Google and search engines, but most of you may not know that a large part of what makes those technologies so powerful is studying the mathematics of networks. And so these are some of the mathematical tools that have been applied in that domain. And suddenly, because I think of this problem in terms of networks, I can apply this mathematics. I wrote a series of papers with my graduate students, starting in 2019, 2020, again, another paper in 2020. And what we were able to do is that we were able to take the equations that describe M theory, and we were first able to sequence them just like you do in genetics. And this is a description of the sequencing process. The next thing we did is, I'm going to remind you that I told you earlier that this value J governs how particles in the real world wiggle when they move. So we can apply this idea in 11 dimensions, but we don't apply it to equations, we apply it to pictures. And so this is a picture that we associate with a thing that moves like a slinky. This is the picture that we associate with the object that moves like a photon. And this is a picture that is associated with objects that move like the graviton. The electron has also has a picture, but it's a picture with a single red box. And red boxes are different from blue boxes in the way that we formulate this mathematics. In fact, we've been created new mathematics to capture these ideas. And so the gravitino turns out to be, as I said earlier, it's just this representation. And there are lots and lots of others because this integer j goes on for this one down this column, every half integer value, in this column, every integer value. So these pictures extend forever. The cool thing about these pictures is that they have multiplication rules built into them. That is, if I take the picture that I see here and multiply that by the picture that you see there, there's something called the Richardson-Littlewood rule that tells me what happens when I multiply them. I get the two pictures on the right side of the diagram. Now, again, this is well-established math. So what we needed from our process was to enlarge this to our domain of blue pictures, blue boxes, and red boxes. Our blue boxes basically are governed by the same rules that are standard for multiplying young doubloons. We had to actually invent rules for the red boxes, but you know, that may sound very funny, inventing math, but we do it all the time. You see, mathematics is so flexible that it's like writing music. People write new music all the time. We write new mathematics all the time. As long as it is logically consistent and doesn't have any mathematical inconsistencies, you can make new math. And that's basically what I do and what my colleagues do in our area. We often have to invent mathematics for our ideas that was not ever there before we had the ideas. And so we extended, we had to figure out how to multiply red boxes, for example, and it turns out that for us, it looks like what you see in this image. You also have to figure out rules for multiplying red boxes times blue boxes, but we also figured that out. And so what we, at the end of the day, is we have a totally graphical way to think about this problem. And we know how to actually build these networks with their rules. These are symbols that just tell us what are the basis that if you start with these red blue boxes, how do you build them to more and more complicated structures? It's just like the rules in genetics. When you look at the 4 base pairs, how do you construct a DNA structure? So we understood that math. And so we needed to write computer programs that worked on our pictures. We applied graph theory and network structures. Those pictures, those box pictures, are associated with a piece of mathematics called Dinkin labels. Their multiplication, so that it's consistent with the left-right balance, requires a mathematical formalism called plethism. And then finally, you just need raw computational power. Why? Because in order to answer the question that we were trying to solve, you have to figure out how the wigglers, so let me put it this way. We know that there are 2,147,483,648 blue wigglers and the same number of red wigglers in order to maintain supersymmetry. But the question is, do you do just, is this like 2 billion single blue boxes? Or are you allowed to write a blue box that has 2 in a row or 3 in a row? How many different kinds of boxes make up this theory? So that's the language that we cast the problem into. And because of the mathematics I showed you here, we knew how to write code to handle every single part of this visual process. And so at the end of the day, we found the object that we were looking at. We found an object that is diamond shaped. I'm roughly showing you what it looks like. And we can talk about it. Here I've talked about it in terms of the numbers that describe its sequencing. We found out that there are 1,198 bosonic fields and 1,186 fermionic fields, and no one had ever figured out these numbers before. The more important thing is that because of the boxes, we knew precisely the different sorts of values of J. In the more precise language of physics, J is called the angular momentum value. So we discovered the explicit angular momentum value for every object that was associated with this 11-dimensional graviton, but we also knew what those fields were. And this is knowledge in my field that has never been known before. So this is just more of the sequencing. We can see the graviton at level 16 in that structure that is actually 32 levels high. We can see the conformal graviton in something that is related to scale symmetry, which I've underlined there. And that object there is the thing that had those three mu rho indices called a 3-form. When we go to red boxes, we want to see if there's a gravitino. And yes, that's at 320. Remember that 320 count that I showed you? Well, there it is. And so our architecture allowed us to get to the complete solution, and we're one step closer to trying to get a solution to quantum gravity in the context of string theory. I'm now closing my talk, and I understand we'll have a Q&A afterwards. I have to acknowledge the teaching company because a number of the images that I have used in this were first created for this course called Superstring Theory, the DNA of Reality, that Kostas mentioned in the introduction. A gentleman by the name of Mr. Kenneth Briggs was responsible for illustrating, in terms of computer graphics, the images that I held in my head, and then we have used them in this presentation. I also have to acknowledge a large list of collaborators, which include fellow faculty members, my students, postdocs, and even my co-author on the book, Proving Einstein Right. So, as I said, it's a tiny step, but we have been able to solve a problem that involves 4.2 billion functions. And this is a problem that has never been solved before. And the way that we were able to solve it, looking back at Mr. Turing, is because we, perhaps by some measure, fall into that category of people no one ever expected anything of. Well, we've now done something that no one else could imagine. And so with this, I end my presentation.
Thank you, Jim, for this very fascinating presentation. So we will soon open the floor for questions, and I would like to especially encourage students to put the questions, and then we'll put this into Jim. So we have Professor Middleton and Professor Drummond that will forward the questions. But before we do this, I would like to introduce a small token gift we prepare for Professor Gates. Let me try to share this. So this is a portrait we commissioned from Ollie Dean, which I think is...
I love it. I love it. Thank you so much. When do I get my copy?
So, so after the meeting, well, I'll ask you the address and I'm going to send it to you.
I love it. Thank you.
Okay, thank you very much. So let me stop sharing this. Yes, so now I open the floor for questions. And again, I want to encourage students to ask their questions. I think it's more important to ask the question than to think whether that's a good question. All questions are good questions.
All questions are indeed good. There actually is a question in the chat that I'd like to address, Kostas.
Yes, go ahead.
Mark Spearing. So let me read the question. It says, fascinating talk. Can you speak to a non-specialist about the significance of the recent muon oscillation experiment and the significance of revealing a fifth fundamental force? So let me start with the first, about the muon oscillations. So the G-2 experiment, as I said, it's really a question about measuring the magnetic properties of muons. And remember, mu particles are basically electrons, except they're 200 times as heavy as an electron. That's the simplest picture to think of what a muon is. And so it's not so, so what has been measured was actually its magnetic property. As far as I know, there wasn't an attempt to measure oscillatory properties, but the magnetic property, it turns out those extra digits that I showed you, remember the diagrams that had the loops in them? those diagrams are the things that contribute those extra digits in that part of my talk where we went through Feynman diagrams. In fact, that's specifically why I wanted to include them, so that I could talk about where the extra digits came from. When you draw these extra diagrams, they are the things that contribute the extra digits. And so this experiment, the first muon, there was an indication actually as early as 2004 that if you studied the magnetic moment of the muon, that it seemed to indicate that there were more particles in nature than the ones that were on my left-right table that I showed you. And so the most recent experiment, oftentimes when you get an experimental result like that, it's a mistake, it's an error. It's an error in the instruments, an error in the misinterpretation. But the latest results on the muon experiment, G-2, more strongly enforce that there seem to be other particles helping the magnetic moment of the muon. So that's why the physics community got extraordinarily excited about the recent announcement. Now, the significance of revealing a fifth force. Let me go back to my transparencies, because there's something in those that I can use to talk about this fifth force idea. And we can do that. Can I share, am I still capable of sharing screen?
You should be able, yes.
Okay. So the question was about the fifth force. Just a moment. Let me go to full screen mode. And then we need to back up a little bit. Okay, folks, this is a picture of all the small particles that we know about in the Standard Model. The gluons, and there are 8 of them, are responsible for the forces between quarks in the interior of protons and neutrons and all hadronic matter. The photon is the thing that tells 2 electrons they should be repelled from each other when they get close. The Z0 is also a weak force carrier, because there are 3 forces in nature: electromagnetic, strong, and weak. The gluons are the carriers with a strong force, photon, electromagnetic, and the weak force has these 4 carriers. And so these, it's something very similar to electrical repulsion, but it's what we call weak charge repulsion. Now, if there's a fifth force, we would expect to add another object to this column. And so that would be the significance of the fifth force in terms of what it means for the Standard Model. It would tell us that there are even more forces than the ones that we see here. So that's the significance.
Okay, James, do you want to ask the first one?
Yes, thank you very much, James, Jim, for that fantastic talk. And let me start by going through questions we've had from the audience.
Okay.
So the first question that we have here. So I think it's about the last part of your talk where you were counting. It says, if supersymmetrical, why do the number of bosonic and fermionic fields differ?
Well, because it's basically because of the wiggling property. Because you might think that the fields have to be the same. But you see, if I have a Higgs particle, it has 1 degree of freedom. If I have a photon, it has 2 degrees of freedom. The W particles have 3 degrees of freedom. And so you don't need the fields to be the same. You have to need the degrees of freedom to be the same. And in fact, in the supersymmetric Standard Model, that's precisely what happens. When you actually count the degrees of freedom, they're equal.
Matt?
Brilliant. Yes, thank you, Jim, for the amazing talk. My mind is completely blown.
I'm sorry.
No. It's seriously a compliment. It was a fascinating talk. So this one comes from David Sapa. I was wondering, what if there is no symmetry? So this could be quite a long answer. What if the math underlying our world is not as beautiful as we would like to think? Is there anyone actually doing research that does not take symmetry into account?
Well, look, if you don't take symmetry account, you can't even do electromagnetism. because it turns out there's a symmetry that underlies electromagnetism also. So if you give up all symmetry, there's no place to actually begin to construct mathematics that looks like our universe. So you have to tell me how much you're willing to give up.
James?
Okay, so here's a general question, I guess also related to the last part of your talk. What role has computer science had in your research?
Computer science, well, first of all, the problem that I had just solved in front of your very eyes could not be solved without a computer. Remember, I told you there are 4 billion functions in this system of equations. And there's no way in the world that a person sitting down, at least no way I can figure out, and no way that from 95 to 2020, no one in the entire physics theoretical community of the globe was able to figure out a way to answer that question. So the first thing that I tell people about computer science is that, especially I tell young people this, that you need to learn how to code, because coding is going to be increasingly important as we study more and more difficult and advanced physics. So that's the first thing. For me personally, I don't actually code in a modern way. By that I mean I don't code with the kind of facility my graduate students do. But in 1969, I actually learned how to code because that was the first time that I had to use a language called Fortran 4, which maybe some people have heard about, but maybe not. I don't know. But but the thing that coding does for you, which is quite remarkable, is if you have to tell a computer how to do a calculation, then you will have to have figured out how to do the calculation yourself in very great detail. And that means that when you start writing the instructions to tell the computer how to carry out the calculation, you have to have completely thought out that process. That is called sometimes computational thinking or algorithmic thinking. And it's my premise that people who learn to do that will be better positioned to carry out the kinds of calculations that I've described in today's presentation than people who have not. And so I have a very simple message that I give to people who ask questions like the one that was asked of me just now. And I'm going to share that with you and show it to you. Share one more time. I'm trying to get this in full screen so everyone can see it. This is what I tell people. Learning to use coding is like the mathematical version of putting on the Iron Man suit. And so I highly recommend, for my own students, I always get them involved in problems. We do analytic stuff, paper and pencil, but I also get my students to understand how to code.
Okay, Matt?
Don't be embarrassed about Fortran, Jim. I code in Perl, so I'm a
dinosaur like me. Okay, got it.
Don't be ashamed of it. So there's a question here from clearly a fan of dark matter. Are weakly interacting massive particles now confirmed in the particle physics community?
No. Supersymmetry. So let's go through that whole supersymmetry thing. As I said, I wrote the first thesis at MIT on this subject in 1977. So I have watched the field from its birth. And as a consequence, in 1984, when people start talking about supersymmetry being detected at places like the LHC, you know, a lot of us who had been studying the mathematics like me said, oh, that would be extraordinarily exciting. But we also understood the mathematics that was proposed for how this was possible. And normally in physics, when you propose a sort of a beautiful mathematical idea, it's not enough just to propose the beauty. You typically have to have some physical motivation for introducing the idea. And in this first generation of what's now called supersymmetric extension of standard model, there was never any real motivation. And as a consequence, in 2006, I wrote a paper, which I'll give you the title, you can go Google it. It's called, Is String Theory Phenomenologically Viable? It was published in Physics Today. And in the article, I explicitly said I did not expect that superpartners would be found at the LHC, because the LHC in its first incarnation would only be probing, let me remember the number. If I remember correctly, I think it was a 70 eV in terms of center of energy. And I see Matt shaking his head, so I guess I got it right. And center energy mass. And the point is that if superpartners were considerably heavier than that, you would never see them at the LHC. And I explicitly said this in the article. I also explicitly said, what if, if I was given billions and billions of dollars and said, go find supersymmetry, how I would invest the money? I said I would look for anomalies and decays, rare processes, and branching ratios, and things like that. And things like that included G-2. And so I had always thought that superpartners would likely be far too heavy to be produced at the LHC. And I still maintain that. In that article, I took a guess that it's around 30 TeV is the number I think is we should be looking for. And that's considerably on the reach of accelerators, even the next generation of accelerators. But the G-2 experiments encourage us that there's something else there to look for. You can use G-2 experiments to put lower bounds on masses for superpartners. And that's what I would urge people who do particle phenomenology, is to look to G-2, look to the Feynman graphs that you generically use to calculate the corrections of the magnetic moment, and then use that to put lower bounds on masses in these things. Because that's how I came up with that number back in 2006, that 30 TeV was probably the right number. The question, however, was supersymmetry in dark matter, so let me go there. It has not been confirmed that the superpartners, in fact, I showed you that left-right symmetry table, and some of the beautiful things in that table was there was a lot of new stuff in the upper left-hand quadrant. Some of that new stuff, people have said, well, one of these particles might be the lightest supersymmetric particle, which would be a weakly interaction massive particle, or a WIMP, which is what a lot of people think is the most reasonable way to think of explaining dark matter in astrophysics. So that was an argument that people developed. It is a logical argument, but the question is whether supersymmetry provides it and what's mass scale. And as we all know, the first run of the LHC didn't find supersymmetry. I said it wouldn't. The second run of the LHC, I was actually asked to contribute an article to Physics World. And in that article, I said, nope, I don't think it's going to come up in the second. And now we're past the second run. And so I tell people, you shouldn't, in my opinion, you shouldn't think that this is the end of the idea. Just work to do better physics, right? I mean, nature's just telling us, okay, you want to know the answer to this question? How good are you on my court, right? I mean, it's like a tennis match or a bet. How good are you humans on my court? That's the challenge.
James.
Okay, so we have a question here from Alexander. You mentioned the need for computational power to solve some of these problems. Do you believe that the prospect of quantum computers may help to advance your research and solve new problems?
You saw that indication with my hands. Look, as I said, I have always been a fan that if you give me sufficiently capable information technology structures, I and other people are going to do great physics. So yes, I very much am looking forward to having practical, realizable quantum computers that can run machine learning techniques. By the way, machine learning is something we haven't talked about, but it's a new techniques that you see much discussed. I must say that back in my youth, when I was programming with Fortran, I also did stuff like run search routines and Newton-Raphson methods. I see that Jim is smiling. And so some of us, or the Runge-Gutter method, some of us remember these old methods for how you solve these problems with coding. And so machine learning looks to me like a really advanced version of these very old ideas. And so I want that. I want quantum computers and I want machine learning because I want to solve these problems.
Matt.
Brilliant. Okay, so our next question comes from YouTube. It's easy to forget that we're live streaming on YouTube. How can an alpha or beta particle leave the matter behind from when it decays neutrally charged?
I'm sorry, how can an alpha beta particle?
Alpha/beta.
Alpha/beta. So during
beta. Okay, thank you. Because those are
new particle.
Okay, an alpha particle is basically a bare nucleus to the helium atom. So it's 2 protons and 2 neutrons. And so the weak interaction, for example, can turn a neutron into a proton because a neutron is slightly heavier than the proton. But because the neutron is neutral, if you turn it into a proton, you have a +1 charge. And so in order to balance charge, you have to introduce something with -1. That's the electron. And it turns out that to balance weak charge, you have to actually introduce a neutrino. And so so the decay of the alpha particle is basically on the basis of the weak interaction. It's a weak interaction byproduct.
James.
Okay, so let me see.
Can I interrupt you? The fact that you guys are getting questions means that people are actually still listening to us?
Yes, they are.
Yes, many people. So the next question is, does the magnetic force only exist due to the motion of charged particles? If so, does magnetism even exist? Is it just a special case of the electric force?
Apparently, the answer to that is no. And the reason we give that answer is because the electron is an elementary particle, which by definition means it has, at least as far as we can tell, it has no internal structure. And yet we know it has a magnetic moment. So if it has no internal structure, there's no place for currents to run in. So therefore, magnetism doesn't necessarily need physically moving currents to exist. And the electron is the proof of that.
Brilliant. Okay, so you mentioned a higher number of dimensionality for M theory. With the 4 relatable dimensions, is there anything you could comment on for the remainder in terms of physicality, or are they purely mathematical?
I am part of a camp I like to call it the refuseniks, the higher dimensional refuseniks, because a large part of my community for the last 40 years has invested enormous energy into studying implications of higher dimensional mathematics for our 4-dimensional theories. And there's nothing wrong with that. But the problem is, there's a very subtle problem that no one ever talks about. So I'm going to explain that subtle problem. When you start with one of these higher dimensional mathematical formulations, and you want to go to a formulation that only has 4 dimensions, you necessarily have to prescribe the method by which that is done. The technical term for that is called compactification. And the problem with compactification is that we have no theory of compactification. That is, we have no way to enumerate every possible way of compactifying a given higher dimensional theory. And so what that leaves us with is actually a deep philosophical problem. Suppose our universe really is described by one of these compactified theories, but that we humans haven't figured out the exact compactification technique that is required to get us from this higher theory to ours. Then that means that we don't even know how to perform the experiments to prove it. You see, it's the ability to count the compactifications, at least in principle, that is totally lacking in every single higher dimensional theory I have ever seen, with the possible exception of something called F theory. But if you look at the generic discussion of compactifications, people say, oh, I want Calabi-Yau, or oh, I want G2. Well, who made you God so that you could pick the compactification technique? The answer is you need to be ecumenical and say, what does nature pick, and how many different ways could nature do that? I know of no one who's ever answered that question. And let me here pay tribute to Shelley Glashow, because he's the first person I know who made me start really thinking about this issue. There was a documentary called Elegant Universe. Brian Greene was the main host. I was one of the talking heads in the program, and so was Shelley. And Shelley was giving real pushback on string theory. And he asked, is it a theory at all? And over the years, I've pondered that question, and I finally figured out that there is a very deep sense that he is right, because until you can classify the compactification techniques, you can't claim it's science.
James?
Okay, so are there applications to your work elsewhere other than increasing our fundamental understanding, for example, in chemistry?
So there are no applications that I know of. However, let me quote a story that's supposedly true about the mathematician Sophus Lie. Sophus Lie is the inventor of Lie groups and Lie algebras. And there's a story that when he did that, he set out to create a piece of mathematics that physicists would never use. Well, guess what, folks? Lie theory is all over the standard model. So I can't say that I know that there's no application of what I do, because Mother Nature is just very extremely clever.
Brilliant. Okay, so this is a challenging one, I guess. I found it peculiar that the search for a supersymmetry actually leads to a much more complex world. Is it conceivable that some new form of supersymmetry actually reduces the number of particles we've experimentally measured, i.e. some of these are different manifestation of an as yet unknown phenomenon? And also, what would be the value of a theory of everything that only a few can understand? In fact, do we know for a fact that our mind can ever actually understand the structure of the world? I've been in some lectures where that's that seems to be the case.
Okay, well, let me start with the beginning of the question, Matt, and then I'm going to ask you to bring me along to the entire question. So the beginning of the question was, could there be something more fundamental than supersymmetry? And the obvious answer is yes. There could indeed be something that's more fundamental. And in fact, string theorists claim they know what that thing is, right? They say it's string theory is the most fundamental, that there's nothing after that. Like I said, I'm ecumenical on these sorts of questions because I have part of my belief is we need to take our cues from nature. And so we push our ideas as far as we can, and then we ask nature to confirm that we're not insane. And then, so the idea, it's not a bad thing to have these unusual ideas, but the thing is, they have to be able to confront observation and experiment. And if they're not that, they're not physics. So that's my position on the first part of that question. What was the second part? Because that was a long and
yeah, it really was, wasn't it? Okay, so what would be the value of a theory of everything that only a few can understand? In fact, do we know for a fact that our mind can ever actually understand the structure of the world?
Well, this brings me, well, let me start with the second part of that question and come back to the first. That is the ability of the human mind. There is a lecture at YouTube that I gave several years ago, and it's sponsored by the Noor Foundation. That's N-O-O-R. And the title of the presentation was something like the Mathematical Mysteries of the Universe, or something like that. I don't remember the exact title. But it turned out that that was, for me, one of the most fascinating discussions I have ever been in, because it turned exactly on this question of what the human mind is capable of. And I would refer the questioner to look for that talk, and it's about an hour long, but it allows me to go very deeply into the subject. I point out several things. One of the things I point out is people often ask, is mathematics really the language of the universe? Because, you know, that's what we scientists use to try to figure it out. And what I say, my answer to that question is, I don't know that that's the case, because to me, the question is mathematics the most capable language that we humans can produce to understand the universe? Because you see, whatever we're doing, there's a duality in the human personality that is often overlooked. I recently asked a friend of mine, were the Greeks aware of the subconscious? Because every single human being is not just the entity that you're interacting with, such as we are currently doing so. And I also talked about this in a conversation with Lex Friedan, which is Friedman, which is another YouTube video. And so when you talk to a scientist about what they're doing, you need to be aware that they too have a subconscious, and they can never escape that subconscious. It's hardwired into their rational mind. And so whatever they're doing, there's this greater part of their mind, there are at least some indications that the subconscious is much more powerful than the conscious mind. There's that part that is subtly influencing what we're saying and doing. And so are we capable of doing something more than that? Well, we don't even know what that part of us can do. So I don't know how to answer that question about whether the human mind is capable of understanding the universe. Because the real question to me then turns is, how capable are our subconsciouses? And we don't even know how to study that, as far as I can tell. We're just beginning that, perhaps. But so that's a very deep and interesting question. Now, there was a first part of that second question, Matt, so take me there.
You're right. So the and the other thing is, what would be the value of a theory of everything that only a few can understand?
Well, suppose that such a theory came about and it produced a piece of technology that allowed humanity never to have fear, never to be hungry, never to be abusive. Suppose that technology, which only 2 or 3 people understood, came from a discovery. Would that be of value to our species, even though no one else understood it? I think the answer is yes. So that would be the value of such a thing.
James?
Great. So here's a question going back to the idea of symmetry, which says, going back to the quotes of Einstein and Turing, is there some case for questioning whether all aspects of the universe are based on symmetry?
Yes, it certainly makes sense to ask the question of how essential the concept of symmetry is to the structure of the universe. I'm going to first quote, for the questioner, I'm going to recall something that Steven Weinberg said in that science documentary, The Elegant Universe. He said that Newton combined the celestial with the terrestrial. And by that he meant one part of Newton's law of gravitation describes falling apples. So that's the terrestrial part. But the other part, use of that equation, Newton's law of universal gravitation, is to understand the way the moon orbits the Earth. So that's the celestial part. And so there is even built into something as, some people might say, as simple as the theory, Newton's theory of gravitation. There's a kind of symmetry principle at work there, a very deep and unusual symmetry principle. So if you're willing to throw that away and say, can we do without it? This goes a little bit back to the question that was asked earlier. It turns out that most of what we think of as physics in some subtle way depends on the notion of symmetry, even before we recognized it as a species.
Okay, maybe now that Matt left, I'll take Cyril. So there's a question from a student. It says, I'm not a physics student, so I'm not sure if this is a good question or not, but I was just wondering if the recent CERN finding around the beauty quark influenced your research.
I'm sorry, I didn't quite understand the question.
The recent findings at CERN about the beauty quark, whether that has influenced your research.
I'm sorry, the beauty quark?
Beauty, yes.
It doesn't directly have implications for what I do.
Okay. James?
Okay, so let me see here. So there's a question here about, you said there are about 2 billion bosons and another 2 billion fermions, an astounding number compared to the few in the standard model. What exactly is the difference between them and the 2000 or 2000 bosons, 2000 fermions field predicted by the theory? Does that mean that for every field there is an average of 1 million particles?
Probably the answer is yes. In the context of M theory, that's what our work indicates. That's probably one reason why the problem has never been solved before, because no one could conceive of such a large number of extra states, is a way that we would say it. They're not particle states we required in order to describe the graviton, the gravitino, and the 3-form when they are not obeying their classical Newtonian laws.
Okay, now there is a question. One of the most common testing grounds for any theory of quantum gravity is the black hole information problem.
Yes.
So what does M-theory/supersymmetry say about this problem? Are there any insights of note that the theories that would be worth keeping in mind for anyone wanting to study the black hole information?
So you mentioned I assume black hole radiation at the end and not black body radiation.
Yeah.
Well, first of all, Stephen Hawking, during my talk, I said was the person most responsible for pushing us to think about simultaneously quantum mechanics and general relativity. And the way that he did that is through his great discovery that black holes actually emit a kind of radiation that we now call Hawking radiation. This result was also uncovered by another physicist by the name of Bekenstein. So it's sometimes called Bekenstein-Hawking radiation. So the first thing that I would tell you is that if you go back and actually read those old papers, they're actually mathematically incomplete. In fact, I used to tell people reading those papers reminded me of grading a lot of physics tests where, homeworks where you tell students prove something and they start at the top of the proof and they write down a bunch of equations. Then they at the bottom and say, therefore. But if you read the paper in both directions, and I see James is actually smiling, if you read from the top down and the bottom up, you find often in the middle of the page there's a jump where there is no logical connection. And that paper by Hawking has exactly that character. At a certain point, there's a thing called a gray body factor. And he simply whole cloth says, I think the answer for that is this. And then he proceeds with his evidence about the emission from black holes. String theory, to my knowledge, and maybe this has changed, well, let me say it this way. String theory was the first mathematical construction that contained elements of quantum mechanics and general relativity where that gray body factor was derived in a certain limit, but derived. And so that's one reason why string theory has such a large support in the scientific community, because again, these are not questions that people typically talk about, gray body factors and Hawking radiation. And now, if people have produced other ways of calculating these gray body factors using other ideas like loop quantum gravity we keep hearing about, then good on them is what I say. But string theory did it first. And so that suggests there's something very interesting and powerful about string theory. With regard to the information paradox, which was the other part of the question, I don't know of any fundamental contributions that string theory has made to resolving the information paradox. I'm aware of the recent work by looking at the page curve, where where it has been suggested there was a resolution, but talking to some specialists recently, I have found out that not everyone even believes that. So the information paradox still seems to be an open question as far as I can tell.
James?
So does supersymmetry throw any light on why there are 3 generations of fundamental particles?
No.
Okay, so now I think this is going to be our last question. It's a little bit different than all the other ones. The question is, could you comment on any personal challenges you have faced as a result of being a minority, and how could the field be changed to be more diverse?
It's a good question, and it's a complicated question. And let me answer it in this way. I have written many times on what I think is the basic mechanism by which my discipline and a lot of academia accomplishes a continuing tradition of being unwelcoming depending on demographic factors. And this mechanism that I've seen, I first encountered personally when I was a postdoc and visiting Stephen Hawking in 1980 at Cambridge. I was in a group of postdocs and we were discussing a problem, and none of us knew the answer. And so I suggested something, and nobody commented and the discussion went on. And then a little bit later, my suggestion was remade with a very slight change by someone else in the discussion group. And all of a sudden, the suggestion was deemed important and in fact allowed the group to get to an answer. Now, this process that I've just described to you is something that my PhD thesis advisor, who himself was an African-American, described to me. And I call it the delegitimization / re-legitimization of new ideas, new innovative ideas. If you don't believe this happens, talk to some of your female colleagues, because I can tell you, I've talked to many, many female physicists, and they have described precisely this mechanism. So this mechanism works at all scales in physics that I've observed, from students in the classroom to young postdocs to beginning professors trying to write exciting papers. I know in my own case, I've written papers. Well, one most spectacular example, there's something called ABJN theory, which many people find very exciting. I wrote the basic equations of that 11 years before the paper ever appeared in the literature. And so it's this process of, in fact, it's the Turing comment at work. Because remember, Turing says people no one can imagine anything of. It's the basic process that our discipline and lots of others have as challenges if you're not considered the normal standard demographic.
Okay, thank you, Jim. I think we're gonna close the event at this point. I think it was a very interesting event with a very interesting discussion. So I'd like to thank also all participants, and especially I'd like to thank Jim for this fascinating talk and also fascinating discussion.
Okay, well, thank you for the invitation. And Kostas, I'm looking for that follow-up invitation where I might visit a group meeting or something.
So I think we will rejoin just the panel in a few minutes. So I think we're going to finish this meeting, but you will receive another invitation just to finish off this.
Okay, so are my obligations here finished, or am I?
Yeah, so here we finish, but in a few minutes, if you can just use the link that it was sent to you.
Okay, I have a 1 o'clock, so.
Yes,
okay.
yes.
Okay, thank you all. And thanks to everyone for listening who's out there.
Thank you.